Our next speaker is Yuriy Reznik from Bright Cove.
Okay, good afternoon.
Close to the mic.
Thank you for the introduction, Alex. And this time it's an afternoon, and I have to warn you, there will not be formulas in this talk. But I will have some pictures and some texts and some numbers, so hopefully it will be informative and interesting. And I also must say that I owe much of the material to Yuriy Sinzana, who is our architect of a live platform, and of course the talk is about mass-scale fault-tolerant live streaming. So with this, let me bring a scope of talk, and what I will start with a very basic example of what live streaming is. Then I'll talk about what it is built on, considering cloud-based deployment of live streaming, and then we will talk about sources of failures in that system, and we'll talk about some of the challenges and how we are solving them to make system robust, scalable, fault-tolerant. So with this, let's ask the most perhaps fundamental question of them all, which is, what is live streaming? And at the very basic conceptual level, you could think of it as a source of video that needs to be encoded, sent over the internet to infrastructure data center, which will take that video, do additional processing, prepare it for delivery, and then again send it over internet to the receiving device. So this is kind of ultra simplistic understanding of what it is. But if we look at kind of specifics, it turns out that things are not that simple. So we, of course, needs to start with live source, and it needs to be encoded. So there is a contribution encoder that starts, then it needs to be sent to cloud data center, which again needs to be sent using some protocol. So there is a protocol of sorts that's used as ingest contribution protocol. Then ingest module passes this to the transcoder. The transcoder converts it to a package of streams that are prepared for delivery. For example, it could be an ABR package of HLS streams. And then those streams will need to be segmented, packetized, manifest needs to be generated as common for today's HTTP-based streaming, and then the output could be segments and as well as manifests, and of course segments could be transport streams or fragment MP4s. The manifest can of course be Dash or HLS. And then a composition of them goes to the origin server, and from there it goes to the CDN. Now, if you notice, I use arrows, and those arrows are increasing in size. That increase in size means higher traffic. And the highest traffic of them all will be between CDN to the players, which, of course, natural. That's how we scale in HTTP world. But interestingly enough, there are also big arrows coming back, which is analytics related arrows, because we need to collect logs and try to understand and make sense of what it is, and perhaps monetize and improve system as it exists. So that's kind of a set of building blocks, and data path as system exists. Again, very simplistic, but let's now start with each of the components and see where the points of failures are. And the first of them is, of course, ingest. And what is shown here is a topology of internet with different tiers of networks interconnected, and you know, the stream that goes to live streaming needs to originate somewhere. And in our world, the customers who might be streaming could be anywhere in this jungle. They could be in their garage streaming, or they could be well-established entities who have high-speed connections, or who could provision bandwidth and have AWS director solve the problem in a permanent way using adequate amount of money. But for somebody else, that's not going to be a solution, so they will stream it from garage, and it will go from one ISP to another, and it will bounce from one way to the other, and eventually it will reach AWS, but of course there will be delays, there will be packet losses, there will be jitters, packets will arrive in reordered fashion, some gonna get corrupted, some gonna get duplicated. So these are the issues that we start with dealing with at the ingest side, and of course that's the just starting point for live streaming. Now, besides, of course, the mechanics of internet by itself, there is also different protocols that could be used to facilitate this ingest. And ironically enough, I have to mention this example of something remarkably archaic and going back to pre-HTTP streaming days, which is called RTMP. The sheer reason this protocol still exists is a miracle, but it's been designed a long time ago, and of course it's been found to be not scalable and not adequate for any large-scale streaming, but remarkably enough it's survived, and it's used these days today as an ingest protocol for amateur-style live streaming, and this is the most popular protocol of this kind. Now, of course, it has many deficiencies. It goes over TCP, which pretty much says that it's not real time. It could retransmit for unbounded amount of time. It bloats traffic, and so on and so forth. So video can stop if you use it. So it's remarkable it exists, but that's life. Now, of course, there are other options, and if you are broadcasters, then there is nothing more native than transport stream. And remarkably enough, you can send transport stream over UDP directly to AWS clouds. Systems have capability to ingest UDP. Now, if you send it over UDP, of course, depends on your connection, you might lose some packets. So that's might not be an option. There are alternatives. You could use UDP with RTP and FECs. There are SMPTE specs describing particular varieties of FECs that could be used in this case, and these are all viable options. But perhaps most recent and most promising, and we had a talk about it earlier today, is SRT, which is actually emerging as a very meaningful protocol for ingest of live streaming, and we're actually members of SRT Alliance, and we think it's a very decent addition to portfolio of existing methods of ingesting video. So if you want to ingest it more reliably, SRT is certainly something we would recommend to use. Now, let me move to next topic, and that will be personalization. And by personalization, I mean SSI, server-side ad insertion. And specifically, it's a server-side ad insertion considering OTT-style live streaming. It's not server-side insertion splicing as it was in broadcast and such. So, and these are two different things. And just to give a pictorial comparison of how complex and sophisticated two different worlds are, on the left I'm showing what I think the adequate representation of live streaming is. It's a kid driving on a tricycle and enjoying and being puzzled by every moment of it, and on the other side, it's a team maintaining race car, where the race car is custom designed. Everything is has to happen in a fraction of a second, and if you lose that fraction of a second, you're gone. And that's pretty much alive in SSI, in live world, and the level of sophistication of what it is just for streaming by itself versus streaming with SSI. And just to kind of get to specifics, by the way, the slides are extremely simplifying it. There is like levels of details which I just cannot go because of time constraints, but I'll try to make sense of it. So if we think about live streaming and personalization of those streams, well, if you don't do personalization, we just enjoyed the using CDN for handling everything. It was taking the largest chunk of data and it was distributing it, it was doing scaling, it was doing it cost efficiently, and we don't have to worry about that scale. CDN takes care of it. Now, if we have to do personalization, at the very least, it will do this personalization at the manifest level. In the worst case, you will also attach bits, and that's much more work. But even if you do it on the manifest level, you have to do it on per customer level. And if you need to do it per each customer level, the benefits that CDN gave you by taking away that scale is gone. Now you need to have as many processes actively working as you have clients, right? And in addition to that, you, of course, if you do personalization, you will have to maintain some database. So there is a considerable and states of each event. So there is considerable amount of data that have to fly, considerable complexity that needs to be added. By the way, some numbers, if you have 1 million of concurrent users, that pretty much translates to about 250,000 of transmit requests for manifest generations, and you know, pretty significant amounts of data that needs to be kind of moved all over. Now, there are some compromised ways to try to solve it. One is to use cohorts, which is basically create groups of users that will have identical customization. So you insert same ad and it goes to a group. Well, but then you don't do it on a per user basis. You probably cannot monetize it as effectively. It's not going to be customized in a perfect way. Well, a better longer term approach is probably to move it all this logic to the edge, but we are not quite there yet. So we still have to do it using traditional infrastructure, cloud infrastructure. Some of it is done with edge, but not everything. So, and let's now go through some additional details of what really is happening when we process ads. Again, this is extremely simplified, and also those of you who work with ads will be kind of looking skeptical on this. But in a nutshell, what is really happening is that we might have a CTE35 marker in the content. When that marker is encountered, we need to augment it with session information, user information, all other information that we basically need to package and send to ad server to figure out what would be the adequate ad for that particular user. The ad server comes back with identified content, and then what we need to do, we need to take that piece of content, right? We need to actually transcode it because it might be in a different format. It's not suitable. It might have different resolutions. Audio level might be totally off. It's certainly not going to be in exactly same format. So there needs to be transcoding done, at least at the segment level. And also there needs to be change of manifest done also. And this is a per stream operations. Now, if you do it in a traditional system, the way to do the splicing will be just to run live transcoder and just inject it, and this is the only way to do it perfectly. Well, with HLS we can cheat. What we can do is we could basically insert discontinuity, and we just adapt the ad segment to match the resolutions, loudness level, and kind of get close enough to what the content should be, but discontinuity helps us to keep the other bits intact. And that's an easy way to do it. But of all these mechanics that I described, in this system, nobody is making money yet. It's just a mechanics to insert the segment in manifest and also push it to the origin server. Now, what also needs to be done, if you think about building complete system, is now you need to collect impressions. And you could collect impressions in a variety of ways. You could try to collect impressions from clients, but guess what? Somebody could use ad blockers. So somebody could put some nasty filters on your web browser, and then you're going to lose those impressions. So the more robust way to do it is to do it from server side, from CDN side, or combine them. But collection of these impressions actually also a pretty challenging thing. You know, if we have just for instance, about 1 million concurrent viewers, and we have about 6 ads per ad break, and we have about 20 impressions per ad, which are kind of typical ballpark numbers. Well, what this all boils down to? It boils down to 120 millions of impressions that you need to collect for that single ad break. So that's a pretty large amounts of data that you need to process, and of course, doing it all with at scale, at reliability is pretty challenging, but it's doable. Now, this goes to the core of the talk, is how to do it not only at scale and handle all the sophistications of and mechanics of ad insertion, but also how to do it in a reliable way. And to make it in a reliable way, the surest way to do it is to introduce redundancy. And if you think about redundancy, the easiest way to think about it is that you just replicate every step in your process and execute it in plurality of copies. And then you switch somehow if one of the passes breaks, right? Now, we can replicate, for example, contribution encoders, put 2 of them. We could have 2 links, 2 contribution links. We could have multiple ingests and transcoders and so on and so forth. Now, what happens in clouds is that nothing is easy to replicate exactly, and nothing is going in a perfectly synchronous way. If your encoders are sitting in 2 different regions, they're not going to be in sync. Even if you travel with the speed of light and you happen to have 2 data centers on 2 other sides of it, it will take about a second to reach from one to another, right? So it is a challenge. Now, there are a few mechanisms in streaming protocols that look like they make things like easier. For example, in HLS, there is a way to specify multiple redundant streams. So the clients could potentially pick which one to use if they detect that one of the streams is gone. But what we found out is that there are different clients. There are clients that could switch between segments that are, between streams that are out of sync, and that's still okay with some discontinuity. And there are some that will just break. They switch between renditions, assuming that those streams are perfectly synchronized. So to use this mechanism, what you really need to do is you need to implement a system that is perfectly in sync, where both contribution encoders have synchronized clock, where transcoders operate in sync, where you have perfect way to execute switches if anything breaks. It is doable, but implementing this synchronization at each step is pretty complicated, and it requires algorithms in the class of distributed consensus type of systems. So there are extra delays that goes there. It's doable. We have these types of system, but it is suitable. In some cases, you just cannot do it otherwise. But what we found out is that in like 90% of practical cases, you can actually do things much easier. And how to do things much easier? Well, do things in a redundant way and let redundant paths to be asynchronous, but then add extra switching block that basically what it does, this is high availability generator, it listens to outputs from two asynchronously running chains, and if it feels that one of them is dead or about to die, what it does, it basically switches to the other by just simple manifest manipulation and just insert discontinuity. That discontinuity, it doesn't, look, if half of AWS goes out, it doesn't happen every day, it doesn't happen multiple times during your streaming session, right? So it's an extraordinary event, and if it's an extraordinary event, it's actually perfectly acceptable to have discontinuity in this case. But if the other path is still operational, you can switch, and it will continue to work, and you could send signal to your operators to see what else failed in the other part, so they can reboot it and restart and keep the other system working. So that's kind of in a nutshell few basic techniques that can be used. We implemented them, and conclusions here is this. If you think about building large-scale live streaming, it's actually a pretty challenging task. Everything fails, and the objective is still to stay alive regardless of this. And some things can be engineered to add redundancies, to add capabilities to switch, but there are some other things that you have to do that not relate to, for example, mechanics of how you execute things. It could be some other things. It could be CDNs insufficiencies. It could be limits everywhere. For example, how many lambdas you can run concurrently. Well, everyone who tried to run it at scale knows this number, right? You reach it at some point, and usually at the most inappropriate moment, right? And basically, the path to survival here is to provision for everything, have multiple failure scenarios, have plan B, C, D, Z, engage third parties that you're working with to stage that event, work with ad servers, CDNs, cloud server providers to make sure you have sufficient capacity. Run load tests and everything. That's not easy, but basically, you need to know at which point different things might fail. And you need to know and test them in isolation and also in combination, because if you run things in combination, sometimes that combination by itself is another source of failure, and usually if things fail, they fail in the orders that cause the composite effect most severe, right? So you basically need to take all those steps. And of course, it is a challenge, but it's a bit less of a challenge than it was a few years ago, thanks to CDNs, live streaming, and some techniques that we described, discontinuities and other things help a lot to make things much simpler. But of course, there is plenty of space for additional engineering and for engineers to use their brains and come up with even more sophisticated solutions. Thank you very much.
Thank you, Yuriy, and we have a few minutes for questions from audience.
So Yuriy, you talked about server-side ad insertions and the scalability issue, and you mentioned edge computing as a possible solution. Is there any reason you did not mention client-side ad insertions as a possible solution to for a scalability issue of ad insertion?
Well, there are ad blockers, things are getting sophisticated on client side, unfortunately, not only by content producers and operators of websites, but also by users who are trying to circumvent this.
Ad blockers during the ad time, what's going to happen to the client? It's not going to show anything, shows a blank screen?
It is
That's not
up
gonna
to,
be-
up to imagination of
That's
that.
not going to be a very pleasant experience either, right?
Or it could be something else. It is up to imagination of next vendor producing ad blocking solution X.
More? Okay.
Thank you very much for the talk. In the last slide, you had a component called the HA generator. And I couldn't help but think to myself, where does that run? And what happens if that fails? How do you make the HA generator resilient and available?
Okay, we have multiple of them.
How are they in sync?
Basically, we have a symmetric bridge of them, so there is always at least two of them. So if one fails on one end, there is another one that could bubble.
Any more questions? Okay.
Just a question on testing this, because of the complexity of the system, and some of it may be running on-prem, some of it may be running in the cloud. How can you actually go and try and test this out at scale, without actually affecting customers?
Well, we operate most of things in cloud, and we usually scale with capabilities of cloud and using all resources that are available. And that's when I mentioned that when we run out of limits of lambdas or other compute resources somewhere in regions, that's the reason why.
One last question. So when you were talking about failures in live encoders, you assumed failure of the encoder itself. What do you do if an input fails? Let's say you have an SDI input that has an issue.
So basically, the listener that I was mentioning, it kind of checks for continuity of input, and there is extra signaling to tell us if it failed before the encoder.
Thank you, and another round of applause.